Hello, science students. This is Dr. B, and this is the Concord Consortium Flood Module, Activity 5, and we're going to start right at the beginning. Future floods. The future of flood risk is complex and being actively researched by scientists. In this final activity, you'll investigate how climate change correlates to projected changes in flood frequency. In other words, if we're going to get more rain, we're probably going to flood more. And hotter weather leads to more water vapor, which leads to more rain. So along with flood frequency, flood intensity, the higher risk of floods, and the impact of floods will also be greater. You will model flood occurrence in a future that includes more extensive human development along waterways, which of course alters permeability, as well as more frequent and extreme rain events. By the end of this activity, you should better able to understand the guiding question: how will flood risks and impacts change over the next 100 years? I know that's a long time to think about, but that's your lifetime and the lifetime of perhaps kids you might have. So, scientists have studied the Earth's climate for years. Climate describes the long-term weather patterns observed in an area. The difference between weather and climate is weather is what you dress for on a day-to-day basis, and climate is what you move for. On any particular day, Florida and Minnesota might have the same temperature, but you move to Florida because the winters are warmer. For almost 100 years, scientists have been monitoring the temperature and precipitation across the U.S. as well as all over the world. Look at the graphs below. The graph on the left shows how the average temperature of each year has deviated from the 30-year average temperature from 1951 to 1980. So about right in here is what they're considering average. So there's not much deviation from average since they've averaged 1951 through 1980 to be the comparison temperature, the average, the baseline. The graph on the right shows how rising temperatures can affect the amount of water vapor in the air and how much precipitation falls to the ground. So if you have more water vapor in the air, like you're in a bathroom with a very steamy shower, you know there's more condensation. The mirrors fog up, and sometimes you can see droplets running down the mirrors. Well, that would be like more water vapor that's condensing outside into a cloud and then eventually raining. The graph on the right shows how rising temperatures can affect the amount of water vapor in the air and how much precipitation falls to the ground. So how many of those clouds represent more water vapor in the air. Clouds are water vapor that has condensed, turned into tiny water droplets, and as clouds hang around for a while, sometimes those water droplets get together and make droplets big enough that they can fall as rain, or snow, or hail, or sleet. Scientists use graphs like this to think about how flood risks and impacts are likely to change over the next 100 years. So let's look at the graph of global temperature anomalies on the left. An anomaly is the difference between the average in a specific year and the average temperature over many years. So in the middle, which they consider average, there aren't many anomalies. Before that, the temperature was below the average between 1950 and 1980. And after that, the temperature increased a lot. Based on this graph, the temperature in the last 20 years has been, let's look at this whole graph here. It looks like it was cooler than average in 1980 and 1940. So the average being 1950 to 1980, 1951 to 1980. And if we look closely at the years that you were probably alive, right in here, these years have been much greater than the baseline or the average set between 1951 and 1980. So it's been getting hotter and hotter and hotter and hotter. So based on this graph, the temperature in the last 20 years has been higher than the 30-year average in the middle, lower than the 30-year average, or the same as the 30-year average. You can choose your answer and check it with the check answer button. According to the image on the right, a 1 degree Fahrenheit increase in temperature leads to 4% more water vapor in the atmosphere. So as the temperature goes up by 1 degree Fahrenheit, the available water for precipitation, or the water vapor in the air, goes up by 4%. So if a typical day is 1 or 2 degrees hotter, there's 4 to 8% more water vapor in the air that's available to make precipitation. How might more water vapor in the air affect the likelihood of precipitation? Well, you can think of it as like your steamy shower. If there's more water vapor in the air, if you're in a steamy room, there's much more likely that water vapor is going to condense on a surface. You might have seen it in a kitchen where you're boiling lots of water for noodles or rice. The water condenses on the windows. That water vapor in the air condenses and becomes a liquid on your windows. Or in a steamy shower, you see that water vapor in the air condense on the mirror and sometimes run down. And you can see how water vapor, when you put more water vapor in that air, it's more likely condense. And condensing water vapor is what precipitation is. If there's more water vapor in our atmosphere, it condenses as precipitation. Usually first as clouds, and then as those clouds hang around for a while, they become rain or snow, and of course all of our clouds don't become automatically drop rain or snow, but the more clouds you have, the more likelihood that precipitation is going to develop. So I believe you have the tools to answer this question. I'll give you some hints here. More precipitation, more water vapor means basically there's going to be more rain or more snow in our part of the world. Let's put hotter temperatures, and let's put water vapor here so the causality is more clear. Causality is what makes something happen. So if there's higher temperatures, there's more water vapor, that means more precipitation, and there's more rain or more snow. And if you have more rain or more snow, what's going to happen? That might end up in a river or lake, and you might have flooding. More possible flooding. That's not the answer, but it's a good start to your answer. Extreme rainfall. Many areas of the United States have recently experienced more extreme rainfall events due to rising temperature. Extreme rainfall can happen when the amount of rain and the storm duration are much greater than usual. We've talked about a particular area maybe getting 15 inches of rain in one day. Usually here in Minnesota, a very rainy day will maybe produce 2 or 3 inches, and that's it. But if you get 15 inches in one day, that's very extreme. Use the Flood Explorer to investigate how extreme rainfall events can affect floods in Silver City. Set the amount of rainfall to heavy, the storm duration to long, and the starting water level to high. Run the model, record the maximum number of acres flooded in question 3 below. So let's follow that first part of instructions. We're going to set it to different levels later, but heavy, long, and high here. So let's go heavy, long, and starting water level high. Let's start our model. Remember, we always have a couple sunny days, then it floods, and it'll go back down. So this is what a typical flood kind of has been usually for rivers around the United States. Floods for a couple days, maybe goes up a little bit above its normal height, but it's not usually a big deal if communities don't have anything built too close to the river. So if we look at the graph here, we can see that the exact point is 1,793. That second point is the y. Remember, we're looking at the y-axis. The x-axis is the number of days. We're not so concerned about that. The maximum number of acres flooded was between 1808, 1811. I'm getting different things. Let's round to 1800. So we'll put 1800 here, and then we'll look at the rest of the directions. I'm going to reset it. Make sure you press reload and not restart, or it'll just rerun the same model. Now we're going to go to extreme rainfalls, very long duration, and starting water level high. So now we're going to max everything out. And we've got new tools here. We've got an extreme setting, we've got a very long setting, and we're still working with water level high. Let's run this and see what happens. I highly encourage you to work with your own Flood Explorer and do your own work here, but you can see how it happens and what to do here in this video. So it takes a while, you can see, in this second scenario for the water to go down. And as we've talked about before, if you have earthen levees, they might be absorbing water. They might basically be turning to mud and might not be as effective in holding back the water if they have to hold back for water for 10 days versus maybe 2. So if we look here, we're a little bit above 3,200 here. I would estimate here's 3,300, so I would say maybe 3,250, 3,275. You can make up your mind. So I'm going to put 3,250, 3,250 acres. And if you don't know what an acre is measures the area of a piece of land. Like I live in a small city lot in St. Paul, and my lot is 1/10 of an acre. In the suburbs, lots might be even 1/4 of an acre. So if you put 4 house lots together, that would be an acre. Here in the city where lots are smaller, you'd have to put 10 lots together to get 1 acre, or 1 piece of land that they're talking about, this unit of land. So imagine if 10 people live on, I think there's probably about 20 people on my block. So 20 people probably live in 2 acres, or 20 families. And if 3,200 acres were flooded, that's a lot of blocks. That's a lot of families misplaced if this is all this area is urban area. So that's something to think about in terms of the impact of floods. So how many days did the Silver City area stay flooded in each rainfall experiment? So we're looking at ranges 1 versus 5, 4 versus 11, 6 versus 15. We saw the last one was like 2, 2.5, 3, 4 days, depending on how you count flooded. So if we count flooded here, it's about 13 to about 1. So 13 minus 1 equals 12. If you want to say 11, we're right around in the middle range here. You can look at your own data and kind of figure that one out. An extreme rainfall event, many places will flood. Which of the following places, if they flooded, are likely to impact the most people? Check all that apply. Now, all these are correct answers if you can explain your answer. Remember, claim, evidence, reasoning. So we're going to make a claim in question 5. Put what areas you think would impact the most people. Then give your evidence. For example, I think the most people would live in the retirement village. That could be your evidence. And you could put your reasoning. For example, retirement villages are usually built to be population dense, so they have a lot of people living in a small area. So if you flooded that particular area, that few acres where the retirement village is, you might displace a lot of people. You could also say an airport, because that affects people in the whole region, not just directly around the airport. You could say Hidden Valley Farms. They produce food for everyone in the region, so if people don't have food, that's a big deal. You could talk about how many parents, if they didn't have an elementary school, would have to think about where else their children could get an education. So that could be your pick. A hospital, of course. That serves probably the whole region or the whole city, so that's important to a number of people. Whatever you choose, make sure you have good evidence. If you want, you can pick something from your map here, and you can also make sure you add some reasoning, like this is why I think this is important. For my example, I might say, not only are there a number of people in the retirement village, they're hard to evacuate because older people often don't get around as well as perhaps younger people, and they might have walkers or wheelchairs. They typically may not own a car, so it may be more difficult to help them evacuate than people who are a bit younger. How might the extreme flood have impacted the people going to school or working at Brookside University? Well, let's go look where that is. Here's Brookside, and it doesn't, if we go back, if we run our Flood Explorer backwards here, so we get to just about the maximum flooding here. So we have the map with just about the maximum flooding, and we look at Brookside. Now, Brookside itself isn't flooded, but if you're a student at Brookside and you live in Silver City, can you get to Brookside? The water is very, very flooded everywhere here. And do you think you'll be able to drive a bridge? Can you find a bridge that isn't flooded so you can drive over to Brookside? Your road here, Highway 8, that you might take over to Brookside is pretty flooded. So you might have the building that you go to class in might be fine, but getting there might be the issue. To make a point, this flood was part of the 1997 Red River Valley flood in East Grand Forks, Minnesota. This is a bridge that obviously no one should be driving on. The bridge deck where you drive your car is well underwater, and even if you try to cross it in a boat, your boat would probably be slammed around inside the structure of the bridge and could tip over and could drown you. So nobody should be crossing this bridge pretty much under any circumstances. So if you lived on one side of this bridge and you needed this bridge to get over to Brookside, you could have some serious problems in extreme flooding. Thanks to the U.S. Geological Survey for the great photo. So now that you know what happens to bridges and roads during floods, you can probably form a good answer to question 7. You can kind of think about what happens to bridges and roads during floods. And even if you're not driving your own car, public transportation still uses bridges and roads, and you might still have a very hard time getting there. Extreme rainfall is not the only issue that people living along rivers will have to deal with in the future. There's something else that might affect the risk of flooding: urban expansion. It's estimated that 83% of the U.S. population lives in urban areas, up from 64% in 1950. So by 2050, 89% of the U.S. population is projected to live in cities. When towns and cities grow, more houses and buildings and roads are constructed. The Flood Explorer has a future map for Silver City based on the urban growth projected 100 years into the future. The future version of Silver City is called Silver Metropolis. On this page, you'll investigate the potential severity of flooding in Silver Metropolis. So, these are permeability maps for Silver City and Silver Metropolis. If you looked on the maps in Flood Explorer, you know red is the least permeable. That's where the most pavement, roofs, sidewalks, driveways, parking lots, areas where the rain isn't absorbed are. The green is the most permeable. That's basically soaks the rain up like a towel in our demonstration earlier in Activity 3. And the yellow is kind of in between. It's medium permeability. We're going to take a snapshot of the new Silver Metropolis. Circle the areas that have changed the most. So let's grab a snapshot here. And if for some reason on your iPad or your device, your snapshot tool doesn't work great, you're welcome to just take a screenshot and write on it in a different way. So I'm going to pick a color that's really easy to see here. And I'm not just going to do a cheesy job and draw a quick circle. I'm going to really carefully outline the areas that have changed. So I see this yellow has gone to red on the map here. Where else has it changed? I've seen all of this south side neighborhood change. Here you can see it's yellow and here it's red. The area above Silver City here has changed. So north of Silver City. And it looks like Hidden Valley Farms got a little bit smaller here, that this changed to yellow, so medium permeability. And if you're sneaky, you can probably find a couple areas. Look right here in the bend of the river. So let's close this up. So all those areas in Silver Metropolis have become less permeable. So the areas outlined in purple have become less permeable because of urbanization. Now, what is urbanization? Well, you're building more buildings. You're making more streets, more roads, more parking lots, more sidewalks, more driveways. All of these areas usually don't absorb water very well. There are some ways to do paved areas. You can use paving stones and leave little cracks for precipitation to get in between, but most people don't do that. They're not very practical to plow or shovel here where it freezes and thaws a lot. But people are still working on ways to make pavement more permeable. But in the meantime, things like roofs, driveways, streets, sidewalks, parking lots. When you get more people, you get more of all of these things that aren't permeable. And if you don't have flood mitigation strategies like rain gardens or making sure your downspouts stay on your own yard and don't go out into the street, your rain downspouts where the rain runs off your roof into rain gutters and then down into a tube, it goes to the ground. There are many neighborhoods working to keep the rain that falls on houses in a particular lot or in an apartment building or office building next to their parking lot may have like a little holding pond to let the water soak in. But most construction doesn't think about that. So perhaps it's something that we need to start thinking about more as we urbanize more areas. So now we're on page 4. Future problems. Will Silver Metropolis flood in the same way as Silver City does now? Is the risk of the flooding the same in Silver City versus Silver Metropolis versus Silver City? Let's compare Silver Metropolis to Silver City to see if the effect increased urbanization has on flooding. First, let's look at the snapshot. It shows a flood in Silver City for a heavy, long rainstorm with a high starting water level. Then run the Flood Explorer for Silver Metropolis map with the same storm conditions: heavy rain, long duration, and high starting water level. And then we need to look at both graphs to figure out which map shows flooding over a larger area. So we're going to go heavy rain for a long duration and a high starting water level. Let's run that and see how many acres we flood. Remember, we've added a lot more area here in Silver Metropolis, that is less permeable, so driveways, parking lots, roofs of buildings, sidewalks. So let's stop this. Which map shows flooding over a larger area? Well, this one shows about 1,800 acres for Silver City. And if we scroll down here, it shows over 2,400 acres. So you can decide which number is bigger, 1,800 or 1,800 or 2,400. Let's examine the graphs for both maps. Which map was flooded for a longer amount of time? So up here in Silver City, it went from about 5 days. It started at 2 and ended at 5. So 5 minus 2 is about 3 days here. We need to let it stop flooding here. It went down quick, but it's a little bit of floodwater still remaining over a long time here. And that may be because all of the ground is saturated and there's less ground that's permeable in this model because of the increasing urbanization. So there's less grassy fields, fewer parks, fewer farm fields. So it looks like it's still flooded at 14 days and it started at about 2, so about 12 days. So this is 12 days in Silver Metropolis, and this is about 3 days in Silver City. So if you look at the graphs for both maps, you should be able to make a good decision about which one flooded more for a longer time. Based on the model run for Silver Metropolis compared to Silver City, who would be at a greater risk of flood damage? Well, let's go up here. We can't really back this one up because it's a screenshot, but we know what it looks like when Silver City floods. Let's look at Silver Metropolis a bit when we back up our, let's see, can we back up our bar here? Yes, we can. So to me, it looks like, having looked at similar conditions in Silver Metropolis, it looks like it's a little bit more flooded here. With the less permeability, it seems like that Silver Metropolis might be at greater risk, but we'd really have to measure. I'm making that decision based on the 2 simulations we ran on the previous page, or we ran previously on this page. Explain your answer to the previous question. Consider both changes in the likelihood of flooding and the people and properties resulting from urbanization. Well, we know that Silver Metropolis floods for a greater number of acres, so more land floods. And we know from our modeling that Silver Metropolis, I'm just going to call it Silver Metro, has a longer duration of flooding. So the water hangs around a longer time. So you can decide which one might be at more risk of flooding. And risk of flooding is to building, it's to people. You can think about all the lost work, the lost days of school. All that plays into what are kind of considered the both the physical damages of the flood, and then what are sort of the societal impacts: lost days of school, lost days of work, people not being able to see their families because they're stuck on different sides of the river and the bridges are all flooded. How certain are you that the people living in the time period that you chose in question number 12 are likely to experience a greater risk of flood damage? Well, we've talked about a number of factors that can affect our level of certainty. One, we've talked about the permeability of the land. So let's think about the flood diamond. permeability is less, so there's going to be more runoff to the river. The topography really hasn't changed, so that's not a big deal. The starting water level may be higher because there's more precipitation. If it's warmer, if climate change has occurred, there's more water vapor, there's more rain, there may be a higher starting water level. There also may be more extreme precipitation. So we've covered topography, precipitation, permeability, and starting water level. We're going to have less permeability. We're going to have more precipitation. Topography will probably be about the same. Starting water level may be higher because of the precipitation. So think about those aspects of the flood diamond and how those aspects make you more certain or less certain about whether Silver Metropolis has a higher risk of flooding or Silver City has a higher risk of flooding. So I'm just going to remind you what the flood diamond is here, and you can use this as a good jumping off place for your, so we can think of one as topography. That's probably not going to change unless you really change the shape of the land somehow. Topography doesn't change. Then we can think of precipitation, or water falling out of the sky, either frozen water or liquid water. We have a lot of frozen water here in Minnesota in the winter. You have permeability, that's part of the flood diamond, how likely it is the water is going to soak in. And you also have water table, which we've kind of talked about as starting water level. How much water is the soil already holding? How much water is already in the river? That's what starting water level means. Consider those factors and when you talk about certainty or uncertainty. So we're going to sign off here on future floods, and we'll see you in part 2 of Activity 5. Thanks so much.